Hello, and welcome to a short video that I'm going to do introducing geometric series. We're going to spend a few minutes talking about geometric series, and some of this we are going to follow back up with once we get back into class next week. So let's go ahead and get started. I want to start by kind of motivating the idea of a geometric series and having us think about some things that are kind of related to the stuff with sequences that we've been talking about in class, and then continue to build on it. So here's just kind of a thought experiment that I want us to run through. Let's go ahead and let's imagine that we have a rope, a string, really just anything that we can measure. And let's go ahead and let's pretend that the length of this string is 1. I'm not going to worry about units. We can think about that as being 1 inch, 1 meter, 1 mile, 1 yard, really whatever distance we want it to be. But let's just consider it to be length 1 unit. All right. Now, what I'm going to imagine doing to this string is I'm going to imagine just cutting it in half. Right? So we're going to pretend that we slice it right about down the middle. That's close enough. So now we've got our 2 lengths of string, each with length 1/2. So I'm going to keep the left side. And now what I'm going to do is over on the right side, I have a string of length 1/2. I'm going to imagine taking that length and cutting it in half again. So now what I have is I have a string of length 1/2, and I've got 2 strings of length 1/4. So I'm kind of going to keep this process going and just see what happens. Just see what happens. So now I'm going to keep this quarter that I have all the way to the right. I'm going to cut that in half again. Well, if I cut a quarter in half, I'm left with 2 lengths of an eighth. If I cut the rightmost eighth in half again, I'm going to be left with 2 sixteenths. If I cut the rightmost 16th in half again, I'm going to be left with a 1/32. And we can see that I can keep this process going on. If I were to cut this in half again, I'd be left with 2 strings of length 1/64, 1 128th, 1 256th, so on and so forth. So I could keep cutting these down and down and down and down and down further and further and further and further. So what we end up with is we end up with a bunch of different strings of different lengths. And from those different lengths, we can actually generate a sequence. So we can take a look at the sequence: 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. And then if we were to keep this going, it would be 1/128, 1/256, 1/512, so on and so forth. So we can kind of see here that if we were just looking for the general term in the sequence, the nth term, that might look something like a 1 divided by 2 to the n. Okay, well that's great and all, but now let's pretend that we screwed up and we want to start putting these pieces back together. Right? So if we want to imagine taking all of these infinitely many terms in our sequence, these infinitely many little pieces of rope, and we wanted to piece them back together, well, what would the length of our rope be? Well, it would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus ... So now what we're doing is now we're taking our sequence, right? What we're going to call a geometric sequence, and now that we're summing all of these terms together, we're creating what we're going to call a geometric series. So notice it's different than a sequence. It's kind of parallels this idea of our Taylor sequence, our Taylor series or our Maclaurin series. We have these infinitely many terms, and we're adding all of them together, right? But we actually know what this should be equal to because of how we constructed the terms in the sequence or the terms in the series. We took our rope of length 1 and we cut it down into smaller and smaller and smaller and smaller pieces. So of course, if we stitch them back together, what we should end up with is a rope of length 1. Right? So to kind of build on this idea just a little bit more, notice how these terms in the sequence were constructed. we started off with a term that looked like a half. And then the next term that we added to a half was 1/4. Well, let's think about how we could get 1/4. We could take 1/2, so that 1/2 that we started off with, and multiply it by an additional 1/2. So what we're doing to get from the first term to the second term is we're doing multiplication by 1/2. Now look at the third term in our series, 1/8. Well, how do we get to 1/8? Well, we can multiply the previous term by an additional 1/2. So we have this original 1/2 that we were starting off with, and then to get the second term, we multiplied by a half. To get the third term, we're going to have to multiply by a half again, which is going to leave us with a 1/2 squared. So really what we're doing to get from the second term to the third term is, again, we're multiplying by 1/2. Now, let's talk through one more of these. The next term is this 1/16. Well, to get this 1/16, we're taking the previous term and we're going to multiply it by 1/2 again. So we're taking 1/2 times 1/2 squared, multiplying it by 1/2. That's going to leave us with a 1/2 cubed. So if we think about how we go from the third term to the fourth term, that's an additional multiple of 1/2. So it seems like as we're going up and up and up and up in the terms that we're looking at, we're just multiplying by additional factors of 1/2. So the most general way to think about a sequence like this is going to be in this type of a form, right? So we're going to have some sort of a number. Let's consider that we start off with just some number. Let's think about it as a. Right? And what we want to do to go from the first term to the second term is we want to multiply it by some other number, perhaps a fraction. Instead of calling it a fraction, let's think about it as a ratio. So to get from the first term to the second term, we can take this original number that we started off with and multiply it by the ratio, let's call it r. So what we're doing is we're starting off with a, and then to go from the first term in our series to the second term, we're going to multiply by this ratio r. And then to go from the second term to the third term, well, we're going to multiply by r again. To go from the third term to the fourth term, we're going to multiply by r again, and that's going to leave us with an ar cubed plus ... Right? So here, what we're calling r is we're going to call each of these r's the common ratio. Right? So what we actually have up here is we actually have a series which is in the form the sum from n equals 0 to infinity. We're starting with a, and to get each of the subsequent terms in the series is we are multiplying these by r raised to the nth power. So this right here is what we call a geometric series. So what's pretty cool about geometric series, or series of these forms, is we can actually figure out what they sum to. It seems like it's this kind of wild thing because we have infinitely many terms that we're adding together, but we can't actually sit around and figure out what they're going to sum up to, right? And the way we think about what these are going to sum up to is we actually have to think about kind of constructing some sort of formula, some sort of an idea, some sort of closed form of the series. So let's go ahead and let's actually ask ourselves, well, what do a geometric series converge to or sum to? So the way that we typically want to start thinking about something like this is maybe thinking through an example, maybe starting finite and then trying to build from there, right? So we already know what this thing that looks like a half plus a fourth plus an eighth plus a 16th sums to, but let me actually use that as a launching point for trying to come up with a formula to figure out what these sum to in general. So let's actually consider the example that we looked at before. So let's consider the sum from n equals 0 to infinity of 1/2 all times 1/2 raised to the n. Right? So we know that this is going to sum to 1. But I want us to just pretend, just for a few moments, that we have no idea that this actually sums to 1. We don't know if it goes to 2, we don't know if it goes to 17, we don't know if it goes to infinity, we don't know what this sums to. So let's just pretend that we don't know this. Right? Well, how could we try to figure something like that out? Well, here's one thing that we could do. We could go ahead and we could start creating something that we call a sequence of partial sums. Right? So what I mean by this is I mean that we can go ahead and we can start looking at our series, and we can, instead of looking at all infinitely many terms, that's daunting, that's a big challenging task, is we could instead just look at the sum of the first couple terms. So for instance, if I wanted to look at something like S1, this would just be the first term in our series. So this would just be 1/2. This right here doesn't tell me a whole lot about what my series is going to sum to. It just tells me that my first term is 1/2. But now if I keep this going, if I look at something like S2, now I have the sum of the first two terms, which is going to be 1/2 plus 1/4. Okay, well we can go ahead and we can actually simplify this. I know that 1/2 plus 1/4 is going to be 3/4. Right? So really we've got two terms added of infinitely many. We still don't have a really good idea as to what this is going to sum to, but we can at least get an idea as to what it's going to sum to. Right. So let's look at S3, the sum of the first three terms. Well, that's going to be 1/2 plus 1/4 plus 1/8. Well, if we go ahead and we try to sum these up, well, what we're going to get here is we're going to get something that looks like 3/4, because I know that the sum of the first two terms is 3/4. And then if I were to add 1/8 to it, that would give me 7/8. So now we're kind of maybe starting to see a pattern. Let's go ahead and let's look at maybe the next two terms, and hopefully like a big glaring pattern should be occurring here. So now we're going to go ahead and we're going to look at S4. Well, that's going to be the sum of the first four terms. So here we're going to have 1/2 plus 1/4 plus 1/8 plus 1/16. Well, if we were to go ahead and add these fractions together, what we end up with here is 15/16. So again, hopefully we're starting to see some sort of pattern occurring. So if we look at the fifth term in the sequence of partial sums, here we're going to have 1/2 plus 1/4 plus 1/8 plus 1/16, and the next term is going to be 1/32. If we add up these five terms, we get the fifth term in our sequence of partial sums, which is going to be 31/32. Right? So now I think we have enough of these to actually really start seeing a pattern, right? So a few things to notice here is that the numerators are always one less than the denominators. So we have 1/2, 3/4, 7/8, 15/16, 31/32. And if we notice what these denominators are, these are all really just powers of 2. So this is a 1/2 to the first. This is a 3/2 squared. This is a 7/2 cubed, or 8. This is a 15/2 to the fourth, 16. This is 31/2 to the fifth. So we've got the denominators figured out. 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth. And I said the numerators are just one less than those. So here we're going to have 2 to the first minus 1, 2 squared minus 1, 2 cubed minus 1, 2 to the fourth minus 1, 2 to the fifth minus 1. So now if we wanted to look even further ahead, And just think about just a general term in our sequence of partial sums. The nth term in our sequence of partial sums looks like it's going to be of the form 2 to the n minus 1 divided by 2 to the n. Or, if we really wanted to clean this up, we could go ahead and we could actually rewrite this as 1 minus 1 over 2 to the n. So give me a value of n, and I can go ahead and I can add up the first n terms in my series just by plugging in that value of n right here. So if I wanted to know what the sum of the first 1,000 terms is, all I would have to do would be to plug a 1,000 in here for n, and I would know what the sum of the first 1,000 terms is. Now, if I want to know what the sum of the entire series is, so the sum from n equals 0 up to n equals infinity of 1/2 times 1/2 to the n, well, I know what the nth term is. That's going to be 1 minus 1 over 2 to the n. But I don't want to know what the sum of the first n terms is. I want to know what the sum of all of the terms is. So here I can just take a limit as n approaches infinity. And what I'm going to be left with is 1 minus, well, as n goes to infinity, 2 to the n goes to infinity. 1 divided by something approaching infinity is going to 0. And we are just left with 1. So that right there is kind of the thought process for how we would handle a problem like this if we had no idea what the answer was going to be. Now, this is kind of a simple case and things end up being fairly straightforward to work with, but what we're going to look at when we come back to class on Monday is a more advanced version of this problem. We're going to generalize this idea of a geometric series quite a bit more, and we're going to learn maybe a stronger formula for finding the sum of terms in a geometric series, and we're also going to learn when geometric series might not converge. So if we look at a geometric series, we might end up getting something that goes to infinity, and we're going to learn when we get something that approaches infinity and when we get something that approaches a finite number. But we're going to save that for a different day, and we will talk about that on Monday. All right, thank you guys for watching, and have a great weekend. We'll catch you later.